Sir, good morning.
Good morning, yes.
Good morning. Sir, another 2 minutes, we'll start. Another 2 minutes.
Good morning.
Good morning, sir. We'll start and we'll wait for another 2 minutes and we'll start.
Okay, fine. Okay, fine.
Sir, please on video. We'll start, sir. Good morning, sir. It's not audible, sir. Sir,
Good
please
morning,
unmute.
yes. Good morning, yes.
Yes, you're audible, sir. Sir, as per your request, we have joined our final year students also in this webinar
Okay,
for today's session.
That is good, actually, yes.
Final year students are there.
Okay.
Just for a short, as the students are here, I'll give a short introduction to you because they are new today.
Definitely, yes. Okay.
I welcome you, sir. Dr. B.V.C. Bhushan Das. He is a associate professor and institute GAN coordinator from Department of Civil Engineering, National Institute of Technology, Surat, Karnataka. He has completed his postdoctoral research associate from Lawrence Technological University, USA. He has completed his Doctor of Philosophy, PhD from IIT Bombay, completed Master of Technology from IIT Delhi, Bachelor of Technology from Kolkata University. Sir is currently Associate Professor in NITK Surathkal. Sir has published, edited 3 books and ongoing is 1. Sir has published 16 book chapters in SCI and Scopus journals. Sir has published 3 book chapters in non-SCI and Scopus and published 27 research papers in SCI and Scopus journals. 9 research papers in non-SCI and Scopus, presented almost 44 research articles in conferences, international conferences and workshops. Sir has completed 5 sponsored projects and 3 are ongoing, worth rupees 5 crore. Sir has been involved in many courses for both in PG level and UG level, construction planning and control, project management, new technologies and materials, construction practice. Sir has completed 4 PhD students and ongoing are 6 students. And sir has been honored with 40 plus awards and achievements. Best Paper Award and many outstanding reviewers award and many more. Sir is a reviewer of many memberships like Life Member of Indian Concrete Journal, ICJ Journal. He is a member of Life Member of ICJ, Associate Member of American Concrete Institute ACI, Associate Member of American Society of Civil Engineers, Associate Member of International Association for Computer Methods and Advances in Geomatics, many more. And he is a reviewer of Journal of Materials in Civil Engineering, ASCE, Canadian Journal of Civil Engineering, Construction and Building Materials, elsewhere publications, and many more. With this, I thank you once again, sir. You have already completed one session for our FDP since Monday, and today is the another session from Bibhiti Bhushan Das, sir. This session is on the research, new researches in sustainable advances and requirements of research in concrete technology in the era of 21st century, which is our final year students can also make use of this presentation. So we have requested our students to join also. We have around 25 students. Commonly, they have joined in a separate classroom. Thank you, sir. Over to you, sir.
Thank you. Thank you, Dr. Momin, for the introduction. So today, I just asked you to include your BTech students, because this lecture is is nothing but kind of a philosophical lecture, and it will help the future generation researchers actually. So before going to the details of the lecture, now I will just give some statistical data here in the beginning. Well, this data actually is from the United States. When I was doing my postdoctoral studies in United States, and after that with some association we collected some of the statistical data actually. Now if you see anyone I don't know how many of you are associated with the American Society of Civil Engineers, very few institutes in India having a student chapter. We are having one of the chapters here at NITK. So if you get the information of United States and just try to compare their budgets for the infrastructure. Budgets for the infrastructure. Well, you may be knowing Prime Minister Modi as when he became the Prime Minister 2014, he had promised the infrastructure budget is going to be $1 trillion. So that is the budget for India is for the newly constructed facilities, means whether it is a road, whether the bridges, maybe it is the public utility facilities, the convention centers, so all other things actually. So that is the $1 trillion almost was the budget for the newly constructed facilities. Now let us see the statistical data for United States of America. Now I don't know how many of you know, US United States got developed in the year of 1960, 1970. That is the time where US got developed actually. So that is the point where they spent trillions of money, trillions of dollar, okay, they spent in building the new structures. Once they built the roads, they built the freeways, they built the bridges, they built the buildings. So it is, so they developed by 80s, they were fully developed actually. So there was nothing else was remaining to be built actually. So by now, so let us assume, okay, like they build, okay, most of the structures by 80s, on an average 80s, okay, 90s, okay, so 80s, okay, let us say 80s, 90s. By now, so by 2020, if you see their budget, their budget is going not, okay, for the building new structures. Their budget is being spent in repairing the structures. So all their budget, okay, all the infrastructure budget from the presidents of United States or whatever, like, is being sanctioned. Recently, okay, there was a sanction also that was for repairing the structures. So why actually? Now there is is a big concern actually. It's a big concern actually, because in spite of, okay, thinking of building new structures, if your all the money is being spent in the repairing structures, now we also need to think about it as a developing country like India, because right now we are moving towards to be a developed country. Now we are in the stage of developing, and we are spending huge amount of money in expanding our infrastructure facilities. So for example, okay, you can see here, like, I have given the, like, 50% of the bridges, like they have around 500,000 bridges actually. So is in distress, means those bridges are not, many of them, okay, are not being used, or many of the bridges needs critical repair. So what is the repair actually cost? This was the cost in 2015 actually, $200 billion, okay, was the cost that time, was only for bridges to repair. Similarly, they have also so many dams actually. 204 dams are having with issue of alkali aggregate reactions. So I hope, okay, you all, okay, because you are already in final year, so you must be knowing about the what is an alkali aggregate reactions. So now the question is, what is the now need actually? Why, okay, like, now the infrastructure facilities built by United States is only 30 to 40 years old. It's not that much old actually. The bridges, the bridges, you know, the service life of a bridge. What is the service life of a bridge? It is around 100 years. We normally design a bridge for 100 years. But now the statistical point of view, what is we are seeing, okay, what is happening in the United States? Well, after 30 years, it is asking for the maintenance. It is asking for the service. So means there is some problem actually. There is some problem. We need to think about it. So means whatever the material is being used for building these bridges may not be adequate actually with the maybe the severe climatic change, or maybe the present climates, or blah blah. So we need to think about the first job is need for materials. Remember, your soil mechanics is not going to change. It is the same, okay, concepts that is going to be adapted. Even your structural engineering, structural analysis is not going to change. It is the same method going to be adapted. But the only one prime thing where there is a need of change is the materials. The materials for the construction. So now, remember, new materials that we should, okay, specify is the green concrete, type of cement that is being used. Recycled aggregates may be high strength concrete, may be low heat generation concrete. So these are some of the possible actually way may give a solution. We don't know actually, but we need a lot of research actually in this particular front to understand the longevity of the materials. Whether these materials, whether the green concrete that you are saying is going to meet the expectations. That is, what is the expectations? My expectation is whatever the design life of the structure has to sustain. That is my expectation actually. So with new materials, now we have to develop, or you have to specify the new criteria. That is, now we have to specify okay, this you can use any materials. Suppose you are now we are saying the sustainable materials, the recycled materials, the low heat okay generation okay concrete, but we have to specify new criteria. That is very much essential now. We have to specify the new criteria. That is maybe a low shrinkage with a crack free, the maximum temperature rise, maybe there is a restriction okay should be put, then architectural concrete, then environmental impact. Now most of the cases you must have seen, now we now at this point of time we are moving towards very much okay fancy constructions. Okay, now so architecture okay is the one who goes for okay like giving the fancy plans. So whether should okay have the criteria whether your concrete is going to sustain that architectural requirements. And next is the environmental impact. Is also is one of the important criteria need to be specified. So now particularly like there are two major challenges in this century okay 21st century, like the two major challenges I feel, that is one is the environmental impact. Now let us see some of the statistics. Now let us see with respect to the concrete point of view, because that is the what is the construction material. Now let us see what is the world demand per year. The world demand per year is 11.5 billion tons of concrete is required now. Now how we are going to produce? Well, for producing 11.5 billion ton of concrete, you need 1.5 billion ton of cement, 1 billion ton of water, and 9 billion ton of aggregates. Now think about where you are going to get this volume of or this quantity of materials. Okay, fine, we will get it. Okay, fine. Let us think about like we will get okay, we will get the materials. Now what is the consequences? The consequence is, well, for 1.5 billion ton of cement, the problem is it generates 1.5 billion ton of carbon dioxide. And you all must be knowing the construction industry is being blamed for 5 to 7% of carbon dioxide production. That is, we call it a greenhouse gas. So the global temperature rise, the one of the like the partial region, okay, partial, okay, like responsibility for the construction industry is 5 to 7%. And remember, whatever the statistical data I am presenting here is keeps on increasing actually with year to year. Now when you did the survey, it was 1.5 billion ton of cement. Now it might have gone okay crossed 2 billion ton of cement. Okay, with time, with year, the demand is increasing actually. So this is the consequence. Now, okay, now the second consequence is, well, this is okay, this presentation okay I've just made okay for so where you are going to get 1 billion ton of water. Well, for a country like India, many parts of country we are not getting water for drinking. So if you are going to supply a significant amount of water for making concrete for the construction industry, how you are going to provide drinking water to the citizens? So we need to think about it actually. But this is one of the consequence. Now, third consequence is depletion of natural resources. Now you must be knowing, okay, there is everywhere news is coming. You cannot mine the fine aggregate from the riverbeds. So fine aggregate is already banned. And remember, another few years, government is going to put restrictions, no quarrying of coarse aggregates. So you have to now think about the alternate materials, even for the coarse aggregate. Even now, you must be doing lot of research we are doing as a alternate material to fine aggregate, that is sand, because it is not easily available. The natural river sand is not easily available. So same case is going to happen. So this is like one of the consequences. So you are depleting the natural resources. Now, next, okay, challenge. Challenge 2 is the long-term durability. So I was just talking about. So what is the meaning of durability? Well, durability is the longevity. It's long life. So long-term durability is a challenge now for the civil engineers. So what is the meaning? Meaning is civil infrastructure is quickly deteriorating. So if your infrastructure is deteriorating, remember, building the same infrastructure is not easy task. It's not an easy task. So you need to think about what to be done actually. Well, in India, I was telling you, the situation is because we are just moving towards being a developed country. So we are spending huge amount of money in building the infrastructure, but most of the developed countries in the world, problem is their civil infrastructure is deteriorating very fast. So that is the challenge actually. Now you can see here on the picture, in Philadelphia in US, you can see one of the column, how it is completely got cracked. And remember, this bridge was completely closed, and 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 remember, like the concept in the United States is they are having a freeway. Means your vehicle, you are moving with a very high speed, and you are diverting the traffic. So it is a big challenge, a big inconvenience to the public. Okay, now why actually the civil infrastructure is deteriorating? Now you need to understand the deterioration phenomena. So when we say the deterioration phenomena, well, I have listed out few, like that is corrosion of reinforced concrete, or one of the foremost in the deterioration phenomena. Then is the sulfate attack, then alkali silica reaction, then also hot and cold weather. Well, in Indian climatic conditions, we are not experiencing much actually, except the complete like northern part of India. Otherwise, we are not having, but we are having a vast coastline starting from the Bay of Bengal to the Indian Ocean to the Arabian Sea. So corrosion of reinforced concrete particularly is one of the biggest challenges to the Indian climatic conditions. And same thing also for the sulfate attack, because our soil, remember, is having a lot of amount of sulfate. So that these two, maybe alkali silica also may not be is not much problem actually in Indian climatic conditions, but these two, the top two, is one of the significant actually deterioration phenomena we need to think about actually. Then Now the consequence, I will tell you what are the consequence now. Consequences is like because of all this deterioration phenomena of around 500,000, that is I was telling you, okay, like 597 340 bridges USA, 73,784 or about 12.4% bridges are structural deficient. So this is the challenge actually. So structural deficient, what is the meaning actually? Meaning is you cannot allow the traffic on the top of the bridge. So means you have to go for a detour. You have to divert your traffic actually. So that is, imagine 12.4% in between 30 to 40 years of the bridges are being abandoned, okay, or are not, okay, structurally deficient. In some of the cases, okay, repair is one of the solution, okay, but some of the cases repair cost is too high. So in that case, you have to just abandon actually, to go for a construction of a new bridge. So this is the one of the consequence, and we also may face immediately actually. So well, we know we need, okay, now at this point is the new and advanced materials. It's a very, very important need of the hour is we need to have, and our next generation should think about doing research in developing a new and advanced materials for our infrastructure constructions. Well, now one such new material is the, I will tell you, is the high strength concrete. Now, you know, the urbanization, particularly we are moving towards urbanization, and most of our, okay, like population will be having a dream, like I will go and stay in my capital city. Suppose you are in Karnataka, everybody has a dream, okay, like I should have a house in Bangalore. Similarly, if you are in suppose Tamil Nadu, they will definitely, okay, have a dream like I should be having a house in Chennai. So now what is the solution actually? Well, the solution is nothing but going for the multi-story buildings, and that is what is happening. Even the small scale cities, okay, like I can see here in Mangalore, okay, like where NIT Suratcal, okay, like is there. Mangalore also nowadays it is going for that, the era is completely a high-rise constructions, multi-story buildings actually. So one such revolution I will tell you in the 90s, 2000 is the high-strength concrete. In the, so because of this development of high-strength concrete by our past, by our previous generation researchers, now you can see there are, okay, skyscrapers, okay, there are, okay, high-rise buildings in the, and the, you know, land is now not available actually, it's very costly, so better to, okay, go for a apartment culture. So now I will give you, like, I will just show you a case study actually how, okay, like this, okay, high strength concrete has made as a revolution, okay, you so so you know, like I think most of you must be knowing this is a twin tower, isn't it? And it is situated in the capital city of Malaysia, that is Kuala Lumpur. It is famously called as the Petronas Tower. One of, in at one point of time, it was the one of the tallest building of the world actually. So I have got, okay, some of the pictures, okay, of the construction of this building, and you will be amazed to see how quickly, okay, these twin towers were constructed with the help of high strength concrete. Remember the material selection was the key actually. The contractor, the client, the architects, they decided, okay, to go for a material like which will give them confidence in building, okay, such a high, okay, like tower. So let us see, like you can see here, like 19 January 1994. This is a like the raft, okay, of the building is getting concreted actually. So concreting is being done in January 1994, and you can keep on seeing, okay. Now uh, just okay, like see the construction is like the superstructure construction started, okay, just kept on moving. So this is one of the picture for April 1994, and you can see, so just parallel to, okay, the one tower, the next tower started actually, and this is a picture, okay, in August 1994, and this is September 1994, and this is October, this is November, okay, like, so you can see the a significant portion of the superstructure is built in November 1994, within the same year of the time actually. This is December 1994. So January to December, you can see the pace of construction, the speed of construction. The speed of construction is very important actually. This is February 1995. Almost you can see the skeleton is almost ready actually. The February 95 skeleton is almost ready actually. And this is May 1995, where, okay, like the finishing and the facade work is just started actually. And this is September 1995, and you can see it is February 1996. It is completed actually. So all the facade work, all the finishing works, all the exterior works is almost finished, except the cleaning of the site. So means it took just, okay, 2+ years, just, okay, about 2, okay, plus years for building such a high tower, such a, okay. Now remember, one of the key material, okay, one of the key thing in the construction is the high strength concrete. So revolution, so the credit is more to the material, because of the material, the pace of construction could go fast. The shuttering, okay, the formwork could be removed earlier actually, as compared to the normal concrete that used to happen. So that is the way. Plus, okay, the lot of, okay, automation, okay, like in like things, and that is the what you can see with advancement of new materials, how we can save our time, how we can save our time and save our resources, save our money. Okay. So let us now see, like, just I have listed, okay, like means let us see, means what actually we know as a concrete, okay, as a concrete, or as a cementitious material, or as a cementitious composite, and what is the requirements and what you can do further. So that's what is the today's lecture actually. So so let us understand the structure and properties of hydrated cement paste. All right. So I know many, okay, like when we like teach, okay, concrete technology to our students, we really, okay, like miss this kind of information to the students. We really miss it actually. So now when you like why actually structure and properties of hydrated cement paste is required. Well, let us now see this graph. Now this graph actually, first let us discuss, then, okay, now let us see. Now this is the x-axis and the right side is 10 millimeter. Okay, 1 millimeter is a log scale. So like that, it has gone up to 0.001 micrometer, that is 1 nanometer. Now yesterday we were discussing about the hydration products. that is the calcium silicate hydrate gels. Okay, now this is 1 nanometer range is nothing but your the calcium silicate hydrate sheets. All right, now what is this side? 10 millimeter is the one actually represents the dimension of our structure. Dimension of our structure. So as I was telling you yesterday, like the whatever you want to tailor, you have to tailor it here in this zone, okay, this nanoparticle zone, nano zone, okay, or maybe in the micron zone. And remember, whatever you want to tailor, you have to tailor it here. And accordingly, the performance is going to show here in the meter scale specimen. So what is the important here? The important is to know in a meter scale specimen or in a nanometer to micron meter, okay, size of the material. It is very, very important to know what is happening in this zone, micron meter to the nanometer zone, because that is what is my microstructure. That is what is my microstructure. And what is the objectives actually? The objective is to learn how the microstructure controls the properties of concrete. So if you have a porosity, there will be a significant influence on the permeability, on the compressive strength, on the all kind of engineering properties. So the important point here is it is nothing but the compressive strength, which is very, very important. Remember, rather than compressive strength, your microstructure and how you are going to control it, how you are going to tailor it, and that is much, much important than the compressive strength. Okay, so again the identify the main crystals present in the concrete. Okay, the main crystals present in concrete. So crystal means, as I was telling you, the calcium silicate hydrate gel, the capillary voids, so nothing but your calcium hydroxide, as we discussed last time, last class, or the last lecture actually. And even you need to understand, like, if there is any kind of agglomeration, okay, agglomeration, and you need to understand the entrapped voids, that is nothing but you are because of the pore, sorry, this is entrained air bubbles. So, and this is entrained air bubbles, so nothing but your what you decide to mix in the concrete at the time of mixing. So that is the entrainment actually. That is special applications of the air entrainment you must be knowing about. And there is again entrapped air void. So this is entrapped air void is nothing but your vibration, okay, actually, because of poor vibration or depending on the vibration, entrapped air void is going to occupy the space. So the important here is like you need to find out or need to understand the how microstructure control the engineering properties of the concrete. Okay. Then the next one of the most important part is in this, okay, like time to understand the transition zone in concrete. The transition zone in concrete. So well, the transition zone I will tell you which is one of the weakest link that affects all kind of properties of the concrete. Now we know we are adding a different kind of materials, whereas like for example we have the steel with specific gravity is 7.8. We have cement, the specific gravity is 3.15. We have aggregates, the specific gravity is 2.5 to 2.6. Isn't it? Even we have a water, specific gravity is just 1. So we have a variety of the materials, like even we going for the secondary cementous material like fly ash, even the specific gravity is very low, it is around 2.2. So you have a different kind of materials. So remember, when you are adding a different kind of materials having different specific gravity, so it is 100% sure there is going to be some transition area, that is transition zone. So means that is defining your material is not a homogeneous material. That's why we call concrete as a heterogeneous material, because there are so many transition zones. So there is transition zone between the aggregate and the cement paste. Again, the transition zone between the concrete or the hydrated cement paste and the steel, isn't it? So there are so many types of transition zones. Even there is within the material like cement to the sand, there will be one transition zone. Again to the cement, sand, mortar to the aggregates, coarse aggregates, again will transition zone. Again as a whole concrete to the steel, because the as a whole concrete specific gravity is normally 2.5 and steel is 7.8. So there will be again a transition zone. So you can see here, there is in the picture here, just I have just given the picture. Now this is the my aggregate, this is the my aggregate boundary, and you have a interfacial transition zone with the cement paste. Now the biggest challenge is how to determine what is the length, what is this length, what is this length, whether it is in millimeter or in a micrometer or maybe nanometer. How we are going to measure it is the key here. How we are going to measure it is the key. And what happens here as compared to the permeability in a bulk cement paste to the permeability of the transition zone, what happens? Because that is what is defining my durability. So that is the way there are a lot of questions arises. So and lot of research has to be done on the transition zone in concrete. Then when you talk about the factors influencing the strength, what is my objectives? Objective is review the main parameters controlling the strength development of concrete. So there are many actually. Just if you see here, like broadly, like I would divide into 3 parts. One is specimen parameters, then the strength of the component phases, then the loading parameters. So when I am saying the loading parameters, stress type, what kind of stress am I applying, rate of stress, and the application of stress, and strength of the component phases. When I'm saying the strength of the component phases, again there are many are there. The matrix porosity, then water to cement ratio, mineral admixtures, degree of hydration, means the curing time, temperature, humidity, air content, entrapped air, entrained air. Then the aggregate porosity, because we have different part of India, we get different kind of aggregates. Somewhere it is basaltic origin, somewhere it is limestone origin, somewhere it is even the marble, like the metamorphic origins. So there are varieties actually. So, and variety of aggregate will have variety of porosity. Then again the transition zone porosity, even the water to cement ratio, mineral admixtures, bleeding characteristics, then aggregate grading, maximum size. So like this, there are so many are there, okay, when you talk about the strength of the component phases. So imagine how much scope is there to do research, to understand what is all these factors influence on the development of compressive strength. Okay, even we have seen the specimen parameters, that is dimensions, geometry, the moisture state. Even like suppose now normally we have seen cube, for a cube we take the 15 centimeter. Now if you cast same concrete in a 10 centimeter size cube, your strength is going to change. We have to have again a correlation. Yes, so because I have done with a 10 centimeter mold, and this is the correction has to be applied. So that is the dimensions. So again, now suppose like, can you go for 20 centimeter like mold? That has to be done. Okay, we have to do research. Okay, why we are only going for the 15 centimeters? So that dimensions. Alright, so specimen parameters also plays a significant role in defining the compressive strength of the concrete or the concrete structures. Okay, then normally, okay, we assume concrete to be a compressive material. It is an assumption. All okay, reinforced cement concrete design, okay, reinforced concrete design, like when you done, you must have okay, like assumed concrete is not going to take in tension. Concrete is going to only okay take the compression. But remember, it is not true, okay, in all the cases. In not all the cases. Now there are different conditions where concrete is going to be subjected, okay, to different kind of stress states, and we need to understand how concrete behaves with different kind of stress states. So let us see, okay, like now what I've done here, I have done okay some more circle, okay, more okay, like circle, okay, I represented okay the stress states in terms of more circles. All right. So let us see now. Now this is one of the biggest okay circle you are seeing, the biggest okay. That is your nothing but your triaxial compression. So means concrete is the best performing when it is subjected to triaxial compression. So my point is, suppose your structure is in a state of triaxial state, and we know concrete is going to perform the best. Now what is the necessity of going for when there is a requirement of M30, so there is no need for going for M40 concrete. All right, so that's why. So so this is okay triaxial compression. The next one is simple, okay, this one is simple uniaxial compression. Simple, okay, uniaxial compression, and that is what actually we always assume the concrete is in this stage. So it's a compression, okay, material actually. All right, and when concrete comes in the category, like suppose it will have a compression tension state, then again performance reduces. And if it is a simple uniaxial tension, almost okay, concrete has no capacity to take any kind of uniaxial tension. Okay, that is need to be understood, and we have to do a lot of research. Well, when we are talking about new materials, green concrete, the recycled concrete, the nanoparticles admixed concrete, sustainable like concrete, sustainable materials like or agriculture waste in the concrete. Well, we need to measure also the various stress states. That is very important actually. Very, very important. Okay. Then the elastic behavior. Well, how many of you know the ingredients of the concrete? The ingredients of the concrete has a different elastic properties than the concrete. Like for example, aggregate. So I have listed it here. Okay, the picture is small. So, so the blue line is nothing but the elastic properties of the aggregate, and the green line, you can see that it is perfectly linear actually. It is a linear aggregate, okay, is linear. Even for a cement paste, it is also very much linear actually. The green line is the elastic behavior for concrete. But you all of know, okay, like the red line, which is completely non-linear, that represents the stress strain state or the elastic behavior of concrete. That is very important actually. We need to understand. Now the point here is, remember when you are specifying any of the new material, any of the material which is not a regular material, where we don't know the properties, it is essential to understand the elastic states. All right, elastic states. But suppose I have seen, okay, like many people, okay, are doing research on the plastic waste. Plastic waste. Now we know it's a elastic material. It's a plastic. It okay, somewhat it is an elastic. Okay, like it behavior okay will be elastic. All right, but when we are using as an ingredient of concrete, we need to measure it. What it gives. We should not predict actually. You cannot predict actually, but you have to measure it. That is very, very important. Okay. Now, another point is, like you can see here, there are, okay, these are some of the pictures here. Now, this is the one, okay, this is the one, this is 2, this is 3, and this is 4. Now, what are these pictures actually? This is nothing but stress strain behavior of concrete under uniaxial compression. Now, the point here is, many times we will have only a proportion of the ultimate stress where concrete will be subjected to. Now, if you see different okay percentage states, now this is the picture okay of 30% of ultimate stress. Concrete is perfect. There is no okay, so no problem except like micro cracks in the transition zone. Similarly, 50% of ultimate stress, no problem except okay there may be some micro cracks in the transition zones. Now, when you are into the 75% the ultimate stress, now you can see there are a lot of micro cracks in the hydrated cement paste, and in a failure stress where it is 100% of ultimate stress, well, the concrete is completely cracked. Okay, concrete is completely cracked. The point here is, what is the important here? The important here is, you can see here now where, see the stress strain is plotted also 1, 2, 3, 4. Okay, you can see here till 30%. Concrete has behaved almost okay linearly. Now beyond 30%, okay, its behavior okay changed into the non-linear behavior. Non-linear behavior beyond 30%. Now, if you have this kind of results, now the idea is you can play better actually with the concrete. But the point is we have to do research. Now, when we're talking about so many kind of materials, so many kind of like variations, but we need to have the informations on the engineering properties, and then only you can better okay manage the new generation materials or the new generation concrete. Okay. Then another important point is the thermal stress. Now, we know, like normally, okay, like we know what is my hydration of cement. My hydration of cement. Now, what we are doing actually, I have seen okay typically like okay there is this kind of waste and it is available, and let us see okay if it is replaced by the cement. Okay, now what we are doing actually, well, I don't know, our mindset is so much biased. We are just okay seeing the compressive strength. Okay, fine. Okay, so compressive strength satisfying. It is coming very good. Done. Okay, done. This can be used as a no. It may not be actually. It may not be. Now, whatever I was speaking, okay, in the beginnings, in the last slides, also applicable. Now, that material, okay, may be responsible for development of thermal stresses. Now, what is the thermal stresses importance? Mostly important it is to the mass constructions like dams, offshore platforms, cathedrals. So mass construction, it is a very mass construction actually. Mass, okay. Now, okay, for building, it may not be okay much, but it is very important point is the thermal stress is lead to the thermal shrinkage in later point of time. So what is important here? The important here is not only okay, you just say okay, yes, initial setting time, final setting time. No, you have to understand the thermodynamics behavior of the material. With time, how okay the thermal load is increasing. Okay, or maybe in the beginning itself, how okay my thermal load, the cement paste. So so normally okay we do analyze with an enthalpy actually. If you can develop okay, determine the enthalpy, and you can determine what is the thermal load or the latent heat. So that is very important actually here. So objective is analysis and control of thermal stresses due to the hydration of cement. Well, nowadays it is not the cement, it is cementitious materials. Okay. Now I've seen like some time before. Okay, I did some consultancy with a industry here where they were producing the cashew nut, okay, cashew nut cell, okay, like cell, and it was a byproduct for them. So they given me this material. They told, sir, can it be used as a replacement to cement? And I checked, okay, yes, compressive strength is coming perfect. So absolutely fine. Then one of my students told, sir, there is strength is fine, but I am seeing there are some shrinkage cracks, very, very miniature cracks. So then we checked it. I realized this material is having some kind of acids, Well, we didn't analyze much, okay, into the properties, but then I did, okay, some kind of durability studies. Then I realized this may not be a right material, okay, to be recommended, okay, as an alternate material to cement. So I just wrote to Pollution Control Board. Well, this contains some kind of material which is harmful to the concrete, because in the beginning point of time it develops some shrinkage cracks because of the thermal load. It is going to be problematic in the future actually. So as a researcher, I cannot recommend this material to be used as a replacement material to cement. So that is the okay key here actually. So many times you as a researcher, you may feel it may satisfying the codal requirements, but if you recommend without satisfying the other properties, at a later point of time, it is going to create a number of conflicts in the site. That's why you have to be very, very careful actually. And understand the properties and the behavior of the material is very important. Okay. Then next is the permeability and durability. Well, I am talking about, okay, in the last slide, last lecture actually, yesterday's lecture. So we need to understand the molecular movement within the cementitious system. Well, molecular dynamics is very complicated actually. As I was telling you till now, we have not done much actually into the molecular dynamics, but we have to now venture into this actually. Well, like we know there is in Delhi, northern part of India, the temperature is very low actually, isn't it? And the temperature is now 3 to 4 degree. Whereas in Mangalore, where I'm sitting now, I'm sweating actually. You can see I'm just sweating. Temperature is 25, 26 degrees centigrade. So that is the variation. But we are specifying the same kind of cement in the both the climatic, even though the climatic condition is too much different actually. So means where there is a freezing condition, I need to understand like what is the structure of ice. Okay, the structure of ice and the structure oriented water molecules in a micropore. So means one place it is getting frozen, you need to understand what is happening there. And other way, you need to understand like, okay, fine, okay, how the water is or the moisture is migrating in the cementitious system. Well, you know, like particularly like the Mangalore climate, okay, like NITK, we're just on the sea. So the structure and the rain is too much here. Rain is too much here. So what is the last thing, you know, how much, okay, like suppose you paint your surface, what is the, you know, what is the like life of the paint here? Just, okay, 1 to 2 years, not more than that. Okay. So this is the, because of the aggressive environments, because of the aggressive ionic movements in the air that is penetrating into the concrete surface or the paint surface and completely destroying the film. So important here is now we need to understand more and more permeability and durability. For a future generation, it is very important to understand the permeability and durability characteristics. Then again, just I was talking about the durability to frost action and fire. Well, you must have got the news Almost every month I see India, like we are reported, okay, India is getting a reported case of fire. Somewhere in Mumbai, somewhere in Calcutta, somewhere in, okay, like in Bhubaneswar, one of the medical, somewhere in Aurangabad, somewhere in Bangalore, okay. So there is there is a fire hazard. Now, when there is a fire hazard, now what happens to the concrete? How concrete behaves? Well, yesterday's lecture, what I talked about the thermogravimetric analysis, we can determine the properties of the concrete in a reverse way. Okay, but we need to understand how, okay, it is behaving. Then same thing, the durability to frost action. Well, as I was telling you, we are not getting actually frost except, okay, the Jammu and Kashmir, Himachal Pradesh, Uttarakhand. So there are few states which are, okay, very critical to the frost action, and how, okay, concrete is going to sustain, okay, going to be durable, okay. So, but but mostly, like many part of the world, it is very critical actually, because they are having frost action actually. So means what happens actually? Now see the picture here. Now this is your pore. Okay, now there is a space here. Now the void space normally, okay, will be the water actually. Pore, we call this as a pore water. Now what happens when it is the water goes into the ice because of the low temperature? What is the sequence? What is the consequence? What is the phenomena actually? The phenomena is there will be a volume increase, the volume expansion. Means if you have given X amount of, suppose X amount of water is there in that pore, that will be 1.08 times X. The moment it converts to ice, it need 8% more volume. Now what will happen actually? Imagine where you will get now this is a picture, okay, just, okay, I have given only one pore space, but in a real time there will be, okay, like one more here, one more here, so there will be millions actually pores. Now everyone suppose want 8% volume, what will happen? They will try to push, okay, the concrete away from the away actually. So a lot of tensile stress is going to develop within the concrete, and the repeated phenomena will lead to the development of cracks in the concrete. Now we need to study, okay, all these things. It's very, very important actually from a sustainability point of view. We are developing, okay, so many varieties of material, but we have to think about what happens to the frost action and the fire. And the fire also is a similar case. Fire also a similar case. When there is a fire, remember the pore water is the one, okay, is going to evaporate. Now evaporate. So it will evaporate, what will happen? It will shrink. The concrete is going to shrink. By shrinkage, so shrink means there will be shrinkage cracks. So that is the way it is going to happen actually. Okay. Then deterioration of concrete by chemical attacks. Okay, so chemical attacks. So the most likely chemical attacks is the sulfate attack and the alkyl silica reaction. So as I was telling you, like most of the cases, our aggregates doesn't have alkyl. Indian climatic conditions, Indian aggregate doesn't have alkyl normally actually. So alkali silica reaction we are not seeing much, but sulfate attack I have seen many actually. So because our soil is having good amount of soil actually, good amount of sulfates, and that sulfate comes in contact with the concrete and starts reacting actually with the hydration products. Well, this phenomena again, okay, is a huge, okay, phenomena actually. 3 to 4 classes are required, okay, to explain. So just I have just, okay, named, okay, only, but but you need to, okay, understand, need to do so much of research on the deterioration of concrete by chemical attacks. And as I was telling you, among the deterioration phenomena, the electrochemical phenomena is one of the most challenging for Indian climatic conditions. That is nothing but your corrosion of steel. So corrosion of steel. So how this electrochemical phenomena takes place is very important actually. Now when you say is a different kind of material, now we know like different kind of material will have different affinity to water, different affinity to even the atmosphere. So how the corrosion takes place with different climatic conditions, different materials is very important actually at this point of time. Then concrete structures in marine environment. Well, now I was just telling we are moving towards urbanization and we don't have space. So what we are doing? We are just going towards sea. Now you must be knowing the Burj Khalifa, that is now representing the tallest structure in the world, also being built on the sea. It's a reclaimed land from the sea actually. So means your structure is just on the sea. Even many cases, like suppose you have a port, the jetties, the dockyards, all they are having continuous interaction with the marine environment 24/7 actually. Now the important here is you need to understand how concrete is behaving, the concrete structure is behaving in the marine environment. So there are a lot of phenomena starting from the reinforced like steel, okay, like that is corrosion of reinforcement to the various type of chemical attacks. Then even the tidal zone effects actually on the structure. Then the cracking phenomena. So there are many such actually phenomena. Now we are unaware of it actually. Even the combined phenomena is one of the another challenge actually. Now there will be so many like phenomena simultaneously acting on the concrete structure. So concrete structure in marine environment is one of the most important phenomena need to be studied actually. So this is just a diagram representation from one of the book. Okay, so you can see here of deterioration of concrete cylinder exposed to seawater. Then concrete aggregates. Now let us now understand the importance of aggregates in concrete technology. Well, we are studying the aggregates, we're studying the aggregates, but as I was telling you, now aggregates is day by day getting scarce. There are guidelines, there are restrictions. So the point here is you have a fine aggregate, but that is not a natural river sand. It is a other kind of material. Now, how it is going to behave in a concrete? Well, your failure pattern is going to change. Well, this new material has adequate resistance. Well, this new material is going to have a good bonding with the paste. So there are so many things actually. Importance of aggregates in concrete technology also need to have lot of attention towards the research. Because we are not much worried when we say, okay, fine, this is the aggregate, okay, just take this ingredient, okay, take this aggregate and produce the concrete. But that is not the case. you need to understand the importance. Suppose you have a limestone. See, I've seen, okay, like I've seen now when I procure the limestone, I see many of the aggregates found to be flaky. I tried to do some work actually on the limestone aggregates, limestone where, see now if you go to the Madhya Pradesh, some part of Madhya Pradesh, the Rajasthan, even some part of Gujarat, they're all full of limestone deposits. Even I think some part of Karnataka also, in northern Karnataka also. So what you will get actually? Everywhere there will be limestone. So for building your infrastructure, suppose you are building a house, you cannot import aggregates from Bangalore, isn't it? It will be too much costly. You cannot do it. You cannot afford it. Whatever the available aggregate, with that only you have to manage. So there is very important to understand the importance of different kind of aggregates in the concrete. Okay. Similarly, the hydraulic cements. So as I was telling you, like we know the moment we add out of the cement, now after 24 hours, cement is going to harden, and 3 days it will give me this much of strength, and 7 days and 28 days, okay, check, yes, satisfying, done. No, you need to understand the microstructure. You need to understand the hydration phenomena. You need to understand the hydraulic cements better. Then only you can be a successful engineer for the next generation actually. Okay, next generation. Because there are so many things happens in the hydration process. Well, this picture is a very like I have given, okay, like from 10 minutes, the moment we add water to the 14 days. How, okay, the cement grains get hydrated. And in this process, what happens? Now, you cannot believe, like, see, this is 18 hour. Now, there is a formation of there is a formation of like AFT, okay, that is your attringite. You might not have, okay, like particularly the students might not be knowing about it. Attringite, we normally miss, okay, in the class. Attringite, even the 1 to 3 days, the same attringites get converted into the AF, that is monosulfates. So like that, when it comes to 14 days we get an CSS. Okay, you can see this is a complete, okay, formation of the CSS. So this is just an example I'm giving from 10 minutes okay to the 14 days. So you need to understand more and more. Even there is a requirement, okay, what happened 10 minutes, maybe 1 hour, 2 hour, 3 hour. So you need, so remember, for understanding all this, for determining all this, you need a advanced characterization techniques. You need advanced equipments. Then only, okay, you can see whatever this picture I'm showing you is being determined through the advanced equipment. So that knowledge is very much also necessary. Similarly, the importance of chemical admixtures. You know, now there is a revolution actually in the chemical admixture, okay, like construction chemicals. So there are so many varieties of chemicals are coming into the market. Now you need to understand each and every construction chemical and what is their influence on the manufacture of advanced concrete. And it is a revolution, it is a blessing, okay, for us actually. But we need to understand them very well. Similarly, the mineral admixtures. So we were talking about, okay, about mineral admixtures since last class. So how okay it is beneficial for us. And the most important part here is the lightweight and heavyweight concrete. It's very, very important here actually to understand lightweight concrete and heavyweight concrete. Well, as I was telling you, there is a requirement of architectural designs. Now, when there is an architectural design, now you need to understand which kind of concrete is going to be perfect. So you need to understand variety of materials, how I'm going to produce the lightweight aggregates, how I'm going to produce the heavyweight aggregates. Even when you go to the nuclear structures and all, you need to design for heavyweight concrete. So there are so many varieties of materials. Actually, you need to understand like from vermiculite, perlite. You can see here expand slag, cinders, okay, sintered, okay, like materials. So many varieties are okay there in the market, and that are being used for producing different kind of concrete. Then the high strength and high performance concrete, as I was telling you, similarly the concrete that is being used for the construction of Petronas towers in Malaysia. So you have to now go for the high strength and high performance also. Not only the high strength, I need the high performance also. Means my service life has to sustain. Or you can say as a green concrete, maybe. Can we like define, okay, can we develop a green concrete which will be high strength as well as high performance? That is most important. Then shrinkage compensating concrete. I was just talking about like maybe shrinkage free can be a criteria, is a question mark. So we have to develop, now we have to do so much of research on the shrinkage compensating concrete. Well, nowadays you must have like seen, must have heard self-healing concrete, isn't it? Self-healing concrete. So similarly, can we go for a shrinkage compensating concrete? We know there is going to be shrinkage in the concrete, a cementitious material. But can my material compensate the shrinkage? Because this shrinkage cracks at a later point of time leads to durability problem. So that's why I am going to develop a cement, okay, cement which can compensate my shrinkage. Similarly, the fiber reinforced concrete, okay, the fiber reinforced concrete is also an area of our study. We know it very well. By adding fibers, there are a lot of advantages. But now we are moving towards so many variety of fibers. Even I have seen the agriculture waste fibers. But you need to study it properly. Actually, what is the percentage of volume and what is my toughness? So that has to be defined properly. Then only you can specify, you can recommend, okay, the new generation materials. Then the mass concrete. So as we were discussing about, you need to understand, you need to learn techniques to minimize the thermal stresses in concrete. Then polymers in concrete. Well, just like the construction chemicals, nowadays so many polymers are there available in the market, and we keep on using the polymers in concrete. But we need to understand whether it is fine to use and it should not have any long-term problem actually defining the durability. So you have to do a lot of research in polymers in concrete. Then the fracture mechanics. Well, fracture mechanics is also very important. How concrete is failing in different modes, like if from aggregate to the cement to the the sand. So all these, okay, so you have a different kind of like failure plans. But how concrete is failing, again, now I was just okay showing you the Morse rupture actually for different okay stress states. So similarly, the fracture mechanism is very important. So you have a different kind of stress, how concrete is getting failed is very important to understand. The last is the NDT, the non-destructive testing methods. Well, there is a lot of advancement. There is a lot of advancement has happened on the non-destructive testing of concrete, and but still a lot of understanding is required. Even though there is a lot of research is being done, but I have seen, particularly in Indian conditions, we are just restricted ourselves with the ultrasonic pulse velocity and rebound number. In most of the cases, 95% cases I have seen the rebound number. Yes, if NDT of structure, okay, rebound number is fine, but it is not the only one which will define everything actually. So there are so many other things are there which we need to know, which we need to learn, which we need to do so much of research in the future actually in the understanding the various properties of the concrete. Okay. So this is the last slide, and thank you for the attention for all of you. And okay, so this is the last slide actually, and now I can take few questions quickly. Okay, like, and now I'm just okay handing over to the Dr. Momin. Yes.
Good afternoon, sir.
Good
This is
afternoon.
Nandar. Participants, if you have any doubt or the question, you can ask to the Das sir, or you can write it in a chat box so that I can convey the question to the sir. Request participant to ask the question in chat box or directly unmute your mic and ask the question. I request Manjunath sir. Any question from the student side? You just take a question and write it in chat box so that I can ask to the sir.
Okay, sir.
Okay, sir. Any question from the participant side?
Okay.
You can just unmute yourself and ask the question, or you can write it in a chat box so that I can convey.
I guess.
There is one question
Yeah.
by
Please.
Dr. Aruna. Influence of materials in high strength concrete mix design. Sir.
Okay. Well, there are. That's what I was just talking about, isn't it? So there are. You have to do. Okay. That's what you have to like do research. What are the influence of materials in high strength concrete mix design? Well, what is the question actually? I'm unable to understand it. That's what okay was the lecture actually, isn't it?
Yes. Yes.
You
Sir.
will have so much of influence, but yeah.
Any other questions? Manjunath sir, any question from the student side?
Sir, no, sir.
No question. Okay, we'll conclude the session here. I thank Dr. B.B. Das for this wonderful presentation. Now I request Dr. Asif Iqbal Momin, FDP coordinator, to present out of thanks as well as present e-certificate as a token of respect. Over to you, sir.
Yes, okay.
Thank you, Naeem. Thank you, sir, for accepting our invitation, and you are ready to accept the invitation and present more than one session. I actually asked you to have one session, at least one in your busy schedule, but anyhow, you were readily accepted to have two sessions with your busy schedule. Thank you for accepting our invitation. We'll be in touch with you, sir, for further any research works or any collaboration works with you. We'll be readily happy to do with you, sir.
Definitely.
Thank you very, very much, sir. Thank you.
It is my pleasure.
This is a small appreciation certificate from our side.
Thank you.
Thank you.
Can you please send it to my email? That is better actually. Okay.
Sir, it is muted.
1 second. No, can you hear me or not?
Sir, please unmute and speak.
Now can you hear me?
Sir, please unmute.
No, it is not muted. It is not.
Sir, you are not audible. Yes. Done. Sir, thank you very much, sir. Hello? Sir, thank you very, very much. We'll be in touch with you for future any collaboration works and any research works with you, sir. Thank you very much, sir. Participants. For participants, we'll